In this video, I'm going to introduce logarithms. Now, to begin with logarithms, I really need to tell you a little bit more about exponential functions. For starters, here's an easy exponential function that you've probably encountered one way or the other. This is simply the function f of x equals 2 to the x. I've picked some values of x and put them here and calculated 2 to the x over here. If these numbers seem a little mysterious to you, then I encourage you to do a little more practice with exponents and particularly with negative exponents and get a feel for how this works. In particular, 2 to the x is very much not the same thing as x squared. 2 to the x is not the same thing as x squared. To give you, again, a reminder of what's going on, in an in a power function, such as, say, f of x equals, I don't know, x plus 5 to the fourth, the variable is in the base, and up here there is a constant exponent. In contrast, in an exponential function, let's say g of x equals, well, I guess I'll still use 2 to the x here. There's a constant base, and the variable is in the exponent. Power functions are all over the place when you're dealing with polynomials and also when you're doing square roots. They're also present when you're doing division because division is power minus 1. But exponential functions are very different from polynomials. They have very different properties. In particular, if you'll notice, for this function 2 to the x, it's always increasing. It's also always concave up, and it has a horizontal asymptote over here going to the left. And these combinations of properties, well, for a power function, you can have concave up and increasing, but with power functions, asymptotes are highly constrained. There's only certain kinds of asymptotes that you can have. And generally, this business of having an asymptote only on one side, that's something that you see in exponential functions, but you generally don't see it in power functions. Now, a couple of other things I should mention about this. Since 2 to the x is an exponential function with base 2, it has the property that every time you add 1 to x, so suppose that I look at x plus 1 up there, I can use properties of exponents to rewrite this as 2 to the x times 2 to the 1. So that's 2 times 2 to the x. That means that if you add 1 to a particular x value, the y value doubles. For example, here at x equals 0, y is equal to 1. If I add 1 to x, the y doubles. So we go to 2. If I'm looking at x equals 1 and then I add another 1 to it, the 2 doubles to 4. So we go from 2 here to 4 here. If I step from x equals 2 to x equals 3, y doubles from 4 to 8. All right, so here's x equals 2, y equals 4. I take a step to the right, but now I've doubled from 4 to 8. Now I don't have it in the table, but if I take another step to the right and go from x equals 3 to x equals 4, y doubles from 8 to 16. So this is different from a linear function where you would have a rise and a run, and if you take a step in x equal to the run, there's a corresponding step equal to the rise in y. That doesn't happen for exponential functions. Instead, if you take a step to the right, the exponential function will grow by some factor. Another thing that we haven't seen yet is what do you do about the inverse of a function like this? Well, remember, here's how to go from the graph of 2 to the x to the graph of its inverse. So I've copied my slide onto a piece of paper, and I've traced the graph on a piece of tracing paper, and I'm going to flip it over. I have interchanged the roles of the axes. I have flipped the graph of the function over the line at 45 degrees, and you can see now this graph is the graph of the inverse of the function 2 to the x. This is a function that we haven't talked about yet in business calculus. This is a logarithm. So let me show you back on the slideshow. The inverse of the function 2 to the x is the logarithm with base 2. The notation for this is log with a subscript 2 to indicate the base. And then I usually put parentheses in this class, and you'll find that the calculator uses parentheses as well. And here you'll see the graph, and it's the same as what I did when I flipped over the piece of tracing paper. What I've done is to interchange the columns of numbers. What this 8 means now is that if I plug in x equals 8, the corresponding y is 3. So let's see here, here's x equals 8 and y equals 3. This is the flip of the point x equals 3, y equals 8 on the graph of f of x equals 2 to the x. The logarithm with base 2 has several important properties. For one thing, it's increasing. It's also concave down. And furthermore, it's only defined for positive numbers. If you'll notice, there's no axis drawn over here for negative numbers as inputs. And instead, there's a vertical asymptote here. Again, what's happened is that all the features of the exponential function with base 2, so the concavity, the increasing, and the asymptote here on the left, those have all been transformed going to the graph of the inverse of the logarithm. The asymptote has moved from here to going down. You can also see in the original 2 to the x function, all of the y values are positive. If you raise 2 to a power, the result is always positive. 2 to a negative power gives you a positive number. It just gives you a fraction. What that means is that when I do that flip and look at the inverse function, the logarithm with base 2, there are no points over here because points over here on the graph of the logarithm would have to come from over here, right? If I say there are no points here, if you watch where my finger lands, oh, can I pick this up? When I pick this up and flip it over, there are no points where my finger is pinching the paper. So the logarithm with base 2 has as its domain only positive numbers. No negative numbers, and 0 is also excluded, excuse me. Now let me say a word about where the word logarithm comes from. It's a very strange sort of word. The log part comes from a Greek word logos. that has a variety of meanings, um, one of which is word, and I'm not sure exactly why they used that, but the arithm is the same Greek stem that you hear in the word arithmetic, and it has to do with adding things. So the deal with the logarithm is that when if you take a number and multiply by 2, the logarithms of those numbers differ by 1. So in other words, if I start with 4 and double it to 8, that's multiplication by 2. The corresponding values of y here are 2 and 3. That's addition of 1. So a logarithm, in some sense, converts multiplication into addition. And that's why the word arithm, as in arithmetic and arithmetic sequence for repeated addition, that's where this word comes from. It was coined, I believe, in the 1600s, 1700s, sometime around there, and we've used it ever since. Now, here is the general definition of a logarithm. You can use any positive number. For our purposes, it only makes sense to use bases that are greater than 1. So you can use any number for your base that's greater than 1. The logarithm with base b of a number u is the exponent m that gives the representation of u as a power of b. In other words, m equals log base b of u means that m is the solution to b to the m equals u. The functions f of x equals b to the x and g of y equals log base b of y are inverses of each other. That's very important because it means that we will now have a tool to undo exponential operations. Now, for reasons that will become clear soon enough, a special kind of logarithm is defined when you use the magic number e as the base. The natural logarithm of a number u is the exponent m that gives the representation of u as a power of e. And the abbreviation for this is ln. And I apologize, I have not been able to find a suitable font that distinguishes all the letters the way I like them. This is a lowercase l and then an n. And so that's the shorthand for logarithm base e. And on your calculator, you will actually see a key labeled ln. Although the key is in uppercase letters, it appears in this calculator right there, ln. And just to remind you, the functions f of x equals e to the x and g of x equals ln of x are inverse functions of each other. And for reasons that I can't really get into in this course, the derivatives of exponential functions and logarithms when the base is e are particularly simple. So even though the number e is sort of counterintuitive, why in the world would you use this crazy number? When it comes to calculus, it's clearly the right choice. Okay, this is the graph of the natural logarithm function. It has a couple of points that I can point out to you. So one is that right here, ln of e equals 1. So you can see this is at 2.7 on the x-axis and then up at 1 on the y-axis. ln of e equals 1 because e to the 1 equals e. Okay, think about that for a moment. ln of e equals 1 because e to the 1 equals e. Likewise, over here, there's a point at x equals 1, y equals 0. ln of 1 equals 0, and that's true because e to the 0 equals 1. Okay, think about that for a minute. ln of 1 is 0 because e to the 0 equals 1. As with all logarithms, the domain of the natural logarithm is positive numbers x. The range happens to be all real numbers, so this part of the graph keeps going down. This part of the graph goes up very slowly, but it keeps going up. It never hits a ceiling. It just keeps going up very slowly, but it keeps going up. Now, a couple of things to notice. Since ln of 1 is 0, and the graph passes through this point, and because the natural logarithm is an increasing function, all of the y values for x's between this 0 and this 1 give y values that are negative. So in other words, if x is between 0 and 1, then the logarithm of x is negative. That's true of any base, but I've drawn it here for base e. Oh, it's true for any base greater than 1. Let me clarify. On the other hand, if x is greater than 1, then the logarithm is positive, and that's what you're seeing over here. The graph is above the horizontal axis, it's taking on positive values, and this happens when x is greater than 1. As I said, e to a power and natural logarithm are inverse functions. So if you have an equation u equals e to the m, you can apply the natural logarithm function to both sides. On the left, you'll get ln of u. That has to be equal to, well, ln of e to the m. The ln undoes the e and leaves you with m. So if you start with this equation, u equals e to the m, and apply ln, that takes you to ln of u equals m. Now, e to a power is the inverse of the natural logarithm. Functions are inverses in pairs. So if the logarithm is the inverse of the natural exponential is the inverse of the logarithm. If I take an equation ln of u equals m, I can apply e to the power to both sides. In other words, e to the left equals e to the right. Well, e to the right is easy enough. This m will become e to the m. ln of u, well, once I do e to the ln of u, that simplifies down to just u. So in this circular diagram, going from the top equation to the bottom is done by applying ln to both sides of the equation, and going from the bottom equation back to the top is done by applying the natural exponential to both sides. A couple of things. We are not multiplying by ln, we are applying the function ln. If you slip and say multiply, you're going to confuse yourself. Likewise, we're not multiplying by e when we go from the bottom equation back to the top. We are applying the exponential function e to the power. So don't say that you're multiplying by e unless you are really multiplying by the number e. If you are applying the natural exponential function, then that's the terminology you should use. Okay. Now, there are a lot of important consequences of this inverse function relationship. I'm going to get into those in another video.